Think about sometimes if you're stuck with something, it's sometimes good to just explore your options. So if I'm looking at toluene, what we've got to do is we need to grow out this chain, right? And so that means obviously we're going to have to do something at the benzylic position. Well, that doesn't leave a lot of options. I mean, you talked last time about the benzylic, the side chain oxidation, right? Treating a benzylic position with potassium permanganate, that would oxidize it to the corresponding carboxylic acid, obviously in this case benzoic acid. Although, I don't know how far that would really get you. What's the other thing that we talked about doing in terms of the benzylic position? Yeah, we could brominate it, right? We talked about that last time and a little bit today. And that might be pretty helpful, right? Because if you're going to grow this chain out, that obviously means you have to make a carbon-carbon bond. And at this point, you don't have a lot of ways of doing that, right? The primary way that you're probably going to make the vast majority of your carbon-carbon bonds at this point is what? Is the Grignard, right? And so if you're going to do a Grignard, then you always need two pieces. You need a halide and you need a carbonyl. Well, if we do benzylic bromination, that gives us one of those two pieces, right? That gives us the halide. So we could do that. Treat this with NBS. That'll put the bromine at that benzylic position, like that. So that's a step in the right direction. Now, if we're going to try to do Grignard chemistry, then that means the other piece that we need is the carbonyl piece. And sometimes when you're doing these, it's helpful, and it also helps you to not make mistakes, to count carbons. You know, I can't tell you how many times I see synthesis problems or mechanism problems where people just randomly insert or delete carbons. It's easy to do, but if you count, if you number, then you'll never make that mistake. So I've got one carbon here outside the ring, but I need 4 carbons. So that means the Grignard that I do needs to include a 3-carbon chain. Because I've got 1 carbon, if I need 4, that means I need an additional 3, right? Simple arithmetic. That's math I can do. So if we're going to do a Grignard and put on a 3-carbon chain, that means we're going to need magnesium. Remember, magnesium does that insertion, and it essentially generates, the way you can think about these is just a carbanion at the carbon holding the halogen. There's your nucleophile. Now we need an electrophile. That's what the carbonyl is for. And if I want a total of 4 carbons, again, that means I need a 3-carbon carbonyl compound. So maybe something like this. The 3-carbon aldehyde. And then, mechanistically what that's going to do is the carbanion, the nucleophile, is going to attack the electrophile like so. You draw the results of that, those couple of arrows. You would initially end up with this alkoxide, which is why at the end of every Grignard reaction you always need a next step H+. All right, so I'm going to just go ahead and do that here. Just put step 3, acidify. That'll give the proton to the alkoxide, and it'll make what you get at the end of every Grignard, which is an alcohol. All right, so now at least my carbon skeleton is put together now. I've got all the carbons I need. That's usually the hard part. Now it's just a matter of just fine tuning, just kind handling the decorative features, just functional group transformations. So what can I do now to make this into that?
Could you do elimination?
Yeah, I like that. So just a dehydration, right? If I just treat this with H plus and heat, that should give me that.
Why doesn't it form the double bond on the other side?
Oh, I was just going to ask about that. Wouldn't I also get this though?
I think so.
Remember what the rule for that is. When you're doing these alkene forming reactions, you can get either a Zaitsev product or a Hoffman product. And the more substituted the alkene, the better. That was that Zaitsev's rule. If you look at these two alkenes, that's a di-substituted alkene. That's a di-substituted alkene. So is either one better than the other?
Does the benzene position the chemical ones or
It does. Normally, you would say no, and you would expect a mixture of products. Because if you're getting two di-substituted alkenes, there's not really one that's preferred over the other. They're equally substituted. But there's something about this pair that makes one of them much, much better than the other. You see what that would be?
Is it the conjugation?
It is the conjugation. If I eliminate in this way, you get a really highly conjugated system, which is going to be dramatically preferred to having some random isolated double bond outside here. Okay? This is a much, much better product because it's a much more highly conjugated product. And that would provide you a pretty exquisite degree of selectivity. So you might have a % or two of this, but the vast, vast majority would be your desired target. Okay. Any questions on how we did that synthesis?
Yeah, can you show us how we get the two long pairs?
Oh, yeah, it's just, you don't technically get that, but anytime you do a Grignard, the actual mechanism is more like when you add the magnesium to the halide, the magnesium does kind of an insertion, and because magnesium is very electropositive, that makes this carbon very electronegative. Right? That bond is highly polarized, and because magnesium's a metal, it's very delta plus, which makes this very delta negative. And the way these Grignards act, they act as if they are carbanion nucleophiles. So you can kind of think, sometimes I'll put that in parentheses because it's not technically a carbanion, but it behaves as if it's a carbanion. All right. Any other questions on the synthesis? Okay, then if not, that is kind of what you're going to be expected to do on the homework. You shouldn't need any more than, I would say, probably 4 steps on most of these. So they're pretty short, just to kind of get us back into the swing of things. All right. Yeah.
How do we add another benzene ring to that?
Well, there's a couple of different ways you could try to do it. You know, if I wanted to add a benzene ring here, you could think about brominating the ring and then doing Grignard chemistry to attack something else. There's multiple approaches you could take. Okay. All right. So let's go ahead and look at the main event for today, which is the directing effects. So we've been spending a lot of time over the last week looking at ways of functionalizing the benzene ring, right? In fact, you just did that reaction last time, right? You took a benzene ring with the combination of nitric and sulfuric acid. You were able to put the nitro group on the ring. And that's fine. You know, and all the examples we've looked at in lecture have been something like this. You take benzene, you add the electrophile, and it gets substituted onto the ring. Pretty simple. Where this gets a little bit more complicated is what happens if there is an existing substituent. Because then in theory, if there's already a substituent on the ring, you're going to end up with, put it down there, you're going to end up with a di-substituted benzene. And as a result, as we know, with di-substituted rings, there are three possibilities. I've drawn it para here, but theoretically I could get meta. I could get ortho. Now, as we discussed a little bit earlier today, if you're going to do a reaction like this, and you're going to get 30% para, 30% meta, 30% ortho, it would not be a great reaction. Because presumably you want one of these three, not the other two, for a synthesis. And that would mean you're going to end up throwing away 2/3 of your product. Even if you were getting a statistical distribution. What I mean by that is you would expect, if you didn't know anything else, we would expect that you'd probably end up with more ortho and meta than para, because you've got 2 ortho positions, 2 meta positions, but only 1 para position. So statistically, you might think, okay, well, I'll probably get twice as much of these 2 relative to that one, just based on the total number of sites. But that's still not great in terms of product distribution. That's still a whole lot of product you're going to end up throwing away. Fortunately, we don't get those types of distributions. We don't get equal distribution. We don't even get a statistical distribution. The existing substituent exerts a particular effect on these reactions. It actually exerts 2 effects. So the substituent will do 2 things. So the first thing that the substituent will affect is the rate. So we have 2 different classes of groups when it comes to the rates here. We have what are called the activating groups. Activators, and as you could probably imagine, these are going to be substituents that speed up the reaction. And as a general rule, these are going to be your electron donor groups. Right. Then we can have the deactivators. And as you can probably guess, these deactivators are going to be substituents that slow down the reaction. And these are typically going to be electron withdrawing groups. All right. Now, I gave you all a sheet that has all of the donor and withdrawing groups on it, but you don't necessarily need to just do rote memorization. Okay, there is a pattern here. The vast majority of electron donor groups, almost all of them are going to be lone pair atoms directly on the ring. So they're most commonly things like oxygens or nitrogens that are directly attached to the ring, right? Because those lone pairs can then delocalize into the benzene ring. They can donate electron density into the ring, hence the name electron donor group. The electron withdrawing groups, these are going to tend to be the pi bond substituents. So most of these, you'll notice, are going to be things like carbonyl groups. If you've got an aldehyde, benzaldehyde, or you've got acetophenone with the ketone, or a benzoic acid with the carboxylic acid, some pi bond substituent directly on the benzene ring. Those are going to tend to be your deactivating electron withdrawing groups. Okay? Now, the other effect that these have, that the substituent has, is the directing effect. So typically whenever you have a particular substituent, it is going to direct the incoming substituent to a particular spot. And we're I'm gonna give you three kind of broad categories here. Two are going to be the major categories, and then there's one exception. All right. So in the main categories, you're going to have the electron donor groups, or the activators, same thing. So the electron donor groups, for the most part, are going to direct orthopara. So the vast majority of the electron donor groups are going to speed up the reaction and direct orthopara. Conversely, the electron withdrawing groups, these, as we discussed, slow down the reaction, and the vast majority of them are going to direct meta. And then, as you know by now in chemistry, there's an exception to every rule. So the exception to this are the halogens. The halogens are, in terms of their rate effect, they are deactivators. Right, because they are very electronegative atoms, and they pull electron density out of the ring. Just not through resonance, but through induction. So they slow the reaction down because they are electron withdrawing groups. Via induction. Yet their directing effect is orthopara. Okay? So they kind of have this weird duplicitous nature. Like I said, the vast majority of electron donor groups will speed up the reaction, direct orthopara. The vast majority of electron withdrawing groups slow the reaction down, direct meta. And then you've got the halogens. They slow the reaction down, yet they direct orthopara. So what I'd like to do now is have a look at a couple of these specific examples and see if we can rationalize both the rate effects and the directing effects. So let's look first, we'll look at an electron donor group. Let's look at anisole. And we're just going to do kind of a hypothetical. I'm just going to say we're going to substitute the anisole ring with generic electrophile. So when we do this, there are three options, as we discussed. We could have that electrophile go in ortho, we could have it go in meta, we could have it go in para. So let's look at the ortho case first. I'm just going to draw these sigma complex intermediates. And I'm just going to kind of draw different resonance forms, just kind of swing the positive charge through the ring and see what we end up with. Now notice, this is a pretty good situation. You know, in terms of a reactive intermediate, the sigma complex intermediate, it's a pretty good situation. The reason it's a pretty good situation is because you have a positively charged intermediate, an electron deficient ring system, but you have an electron donating group. So that donor group is helping to stabilize the positive charge. By the presence of this electron donor group, it makes this ring not quite as electron deficient as it would be otherwise, because the donor group can pump electron density into the ring. That's what is responsible for the rate effect. Because of the electron donating group, it helps to stabilize the sigma complex intermediate, and thus it lowers the energy of this intermediate. So that's responsible for the rate enhancement, because the sigma complex intermediate is lower in energy than it would be otherwise. And these aren't insignificant rate enhancements. To give you some specific data, when you try to do these EAS reactions with anisole, this occurs about 400 times faster than for benzene. So it's pretty substantial. Now, if you look at the three resonance forms that I drew, I like one of these better than the others. Anybody have a preferred resonance form here?
The last one.
Yeah, I like this one, because it puts that positive charge directly under that electron donor group. In fact, when you have this resonance form, it actually allows me to draw a fourth resonance form, right? I mean, I can draw a fourth resonance form where you get that. So that is a very favorable resonance form, having that positive charge directly underneath the strong electron donating atom. So let's go ahead and see what happens if we do a meta substitution. Positive charge would end up there in this case. And again, I'm just going to kind of swing it around the ring. So you'll notice in my meta resonance forms, I never get that really highly favorable resonance structure that puts the positive charge directly underneath the donor oxygen. So I mean, it's still, these are all still pretty good resonance forms, generally speaking, because you've got a strong donor group on a positively charged intermediate. So they are stabilized, more stabilized than they would be otherwise. So the rate is still fast, but it's not quite as good as with an ortho, because we don't get that really nice resonance form. All right. Well, let's see what happens with para. And I don't think we need to go through and draw all of these resonance forms, because I think it'll be pretty apparent here which one. So that would be the initial resonance form. And then again, just kind of swinging the positive charge to the ring, you can see that pretty soon we get to that really good one. Right there. There's that really good resonance form again. So the substituting ortho and para are the only types of substitution that give rise to that highly favorable resonance form. All right. Any questions about that? So that's the source of the directing effect. When you have these strong electron donating groups, you want to be able to put that positive charge directly underneath the donor group, and that only happens when you substitute ortho or para, not meta. So let's go the other direction. I'm going to cheat a little bit. All these resonance forms are going to remain the same. The only thing that's going to change is the substituent group. So I'm just going to, so I don't have to rewrite all of that again, I'm just going to erase the methoxy and stick in an electron withdrawing group.
So the methoxy is the electron zone.
Yeah, methoxy is a donor group. And if you're ever unsure, go back to these general guidelines. The vast majority of the substituents will fall into one of these two categories, either a lone pair atom or a pi bond substituent. And so with the methoxy, you have an oxygen directly on the ring. It's a lone pair atom, which would make it an electron donor group. All right, let's do a strong withdrawing group. Let's do nitro. By the way, you can see this also fits into those guidelines I gave you. A nitro looks like this. So it is a pi bond substituent. Okay, the first thing to realize here is that all of this is bad. All of this is bad because you're talking about a positively charged intermediate, or said another way, an electron deficient intermediate, and you've put on there a strong electron withdrawing group. So you've taken that positively charged intermediate and you've made the situation worse, because you're even pulling more electrons out of the ring. You're making the ring even more electron deficient. So none of this is good, which is why the reactions tend to be so slow. By having that electron withdrawing group on the electron deficient ring system, it really raises the energy of these intermediates. Okay, so that said, one of these is probably use the same logic that you used in the previous example, but one of these is worse than the rest. I think you can really see it when you actually draw out the resonance or the Lewis form of the nitro group. See that third resonance form? How it has the two positive charges adjacent to each other? I mean, when have you ever seen a resonance form like that? Probably never. If you did, it was probably wrong, because that is a very, very high energy resonance form. Having those two positive charges right next to one another. Okay? Really, really quite terrible. If you look at the meta situation, again, none of these meta situations are good. They all involve strong electron withdrawing group on an electron deficient ring, but if you had to choose one, you're going to choose the one that hurts the least, and that would be the meta, because you'll note that none of these meta resonance forms have that really awful one. And then you can see in the para, you get to that same really terrible resonance form, where the positive charges would be right adjacent to one another. So when you have these strong electron withdrawing groups, these deactivating groups, they will tend to direct meta, because meta substitution avoids that very, very high energy resonance form. Okay? Any questions on this? All right, well, let's go ahead and quickly look at the third option, the exception. What happens when you have halogens? Oh, by the way, just to give you a little bit of more specific information, when you try to do these with nitrobenzene, they tend to go 100,000 times slower than benzene. So a pretty serious rate effect with these strong deactivators. Okay. All right, let's see what happens with the halogens. Again, I'm just going to erase the substituent and put in the new one, because all of those resonance structures are going to be the same. Let's do chlorobenzene. So as I said earlier, the halogens are deactivators. Because they're so strongly electronegative, they're pulling electron density out of the ring, making an electron poor system even worse. Right? They're just pulling out, instead of through resonance, they're pulling out through induction. So they are deactivators. They slow down the reaction. But the reason they're different is because these deactivators have something that none of the others had. What does the halogen have that none of the other electron withdrawing groups have? Yeah, the lone pairs, right? The vast majority of the electron withdrawing groups are all pi bond substituents. They pull electron density out through resonance as a result. All the halogens have a bunch of lone pairs. And as a result, I can draw that third resonance form, or the fourth resonance form rather. I can draw another resonance form here where the chlorine pushes its lone pair density into the ring and helps to stabilize the positive charge when it's ortho or when it's para. You do not get that resonance stabilization if you substitute meta. So that's why we kind of see this weird behavior with the halogens, because they have counteracting inductive and resonance effects. Inductively, they're pulling electron density out, slowing the rate of reaction. But because they have lone pairs, they can help to stabilize the charge as long as the substitution occurs ortho or para. Does anybody have questions about that?
That just looks kind of weird.
What's that?
I just said that just looks kind of weird.
I know, you don't often see a halogen with a positive, do you? So let's see how we're going to use all this. We want to use this ultimately to predict products of reactions. So let's say I gave you let's do this. Okay, before we start, what kind of reaction am I trying to do here? What am I trying to put on the ring? Yeah, we're trying to brominate it, right? These are bromination conditions. So we're trying to put a Br onto the ring. The question is, where does it go? Now, I haven't exactly told you about these guys. The halogens are also kind of an exception. Or sorry, not halogens, the alkyl groups are also kind of an exception. Because you'll notice they are not lone pair atoms. They're not pi bond substituents. So they're kind of doing their own thing. The alkyl groups are also donor groups. But they're not electron donating through resonance like all of the lone pair atoms, but they are inductively donating. And that's why if you look on that sheet that I gave you, I think it lists the alkyl groups as activators, but I think it kind of puts a caveat there, and I think it refers to them as weak activators. And that's because they're not activating through resonance, they're activating through induction, which is a weaker effect. Okay. But in any case, they are activating groups, and they are orthopara directors. So if we were to predict the product of this reaction, we would expect major product to be orthobromo and parabromo. Any questions on that one?
Professor, you said the alkyl groups, are they activators or deactivators?
They're activators.
Okay.
Yeah. They're weak activators, but they're activators.
Okay, thank you.
Any questions how we did that? How we predicted the products of this reaction? All right, so when you have a substituent on the ring, it's pretty easy to predict what the major product is going to be as long as you're aware of this. You know, the donor groups tend to be orthopara, the withdrawing groups tend to be meta, and then there's the halogens. So as long as you know that, you can pretty easily predict what major products of these reactions are going to be. Where it gets a little bit complicated is if you have more than one substituent. So let's say we had two things on the ring. So let's do this one. Okay, so the question, what kind of substituent is the hydroxyl? Is this an activator or deactivator? Was it? Yeah, it should be an activator, right? Because it's an oxygen directly attached to the ring. It's a lone pair atom on the ring, so that should be an activator. As such, the activator is trying to direct ortho and para to itself. So it's trying to direct here to that ortho position or here to that ortho position. It can't direct para because the para position's occupied. What about the ketone? Is this an activator or deactivator?
It's a deactivator.
It's a deactivator because it's a pi bond substituent. So as such, it's trying to direct meta to itself. So that would be there or there. Well, isn't that convenient? Everything's directing to the exact same place. So we would expect the major product here, not surprisingly, to be that. Everything's directing to the exact same place, so that's where it goes. Any questions on that? All right. Let's switch it up a bit. What if we had this one? Well, we already said the hydroxyl was a strong activator and thus is going to try to direct ortho-para to itself. So this is similar to the example we just looked at. It's going to try to direct ortho to itself. It can't direct para to itself because, again, the para is blocked. What's the alkyl group?
Activators.
Yeah, it's an activator, albeit weak. It's still an activator. So that means it's going to try to direct ortho-para to itself. Well, just like the other one, it can try to direct ortho, but the para position relative to the methyl is blocked. So now we have competing directions. So how do we handle this one? The rule is, and it's probably not too surprising to you, the stronger activator wins. The hydroxyl group is a much stronger activator than the methyl, and so that's where we would expect the directing effect to occur. So our product we would expect to be
What if there was like a nitro group and a hydroxyl group? Which one would be stronger in that case?
stronger activator wins. So because the nitro is a deactivator,
Oh,
it wouldn't really play play a
Or
role.
what if it was a NH2, another activator like that?
Yeah, when you have a competition between two strong activators, you're going to get mixtures. Yeah, it's hard to predict or control in those cases.
Are all activators, even the weak ones, stronger than the deactivators?
Yes.
And
Yeah.
the deactivators?
Because it's a rate thing, right?
Okay.
So even with a weak activator, that reaction is going to happen a lot faster than certainly a strong deactivator, you know? Okay, I want to give you one more. What if we did this? So it's gonna be similar to this one that we already looked at. We're just gonna move things around a little bit. Let's do this. So we've already established the directing effects of these two substituents. We know that the hydroxyl is a strong activator, it's an ortho-para director, so it's trying to direct ortho to itself, or para to itself. All those positions are available. And then the ketone, as we said, was a strong deactivator, a meta director, so it's trying to direct meta to itself. It can't direct meta in a clockwise sense because that position is occupied, but it can direct meta in a counterclockwise sense. Wasn't that a mess? You have directing effects to every carbon that's not occupied. Even if we go with the stronger activator wins, that still, that takes the meta director out of the equation, but that would still suggest the possibility of three different products. Do you think all three of these would occur in a roughly equal proportion? Do you like one of these better than the others? Do you dislike one of these more than the others?
I like that one for naming.
You like the one on the end, what? Which one?
For naming, when you name the.
Oh. So what do we think in terms of the product distribution?
First one looks nice.
Let's go first with which one do you like least? Why do you say the last one?
Because it's all stereotypically right.
Exactly. That's not going to be likely. Anytime you're trying to sandwich a new incoming substituent between two existing ones, it's not likely. It's just sterically not favorable. So this guy, you would probably see very, very little of. What about the other two options? You gotta be ortho to something here. Do you think it would be better to be ortho to hydroxyl or ortho to the ketone?
I think my first thought is the middle one, because on the first one you have like two strong donating groups right next to each other. I feel like that might conflict.
Well, it's not really where the product ends up. It's more so kind of the formation of that we're looking at. And so in a case like this, you're still kind of comparing sterics, right? So if you think about it, chlorine is not a small atom. I mean, it's decent size. It's in group, what, 2, 3, I don't know, somewhere. It's not small like the size of nitrogen or something. But so if you're trying to squeeze it in right next to a hydroxyl, or squeeze it in right next to a methyl ketone, well, a hydroxyl is pretty tiny. Oxygen small, hydrogen is almost non-existent. That's a lot smaller than this big ketone with a giant methyl group attached to it.
Couldn't that rotate so that the oxygen was out of the way a little bit more? Not so much?
I mean, it could, but there's still freedom of rotation about that bond, so it's kind of swinging like a propeller.
Okay.
So it would still, regardless, it would still be a little easier to fit it in here next to that tiny hydroxyl versus the methyl ketone. And so, but I mean, realistically, you would probably see both. But if I were gonna bet, say we see more of that one. Oh, no, sorry, just kidding, more of that one. But when you start getting into these things with multiple substituents and multiple competing effects, you can do your best to predict, but realistically, you will see mixtures.
So in this example, the most favorable product has to do with sterics and not because one is an activator and one is a deactivator?
Yeah, because the electronics is already set.
Okay.
We've already determined as much as we can with regards to the electronics, because we said that the stronger activator wins. So we, based on that, we got rid of the effects of the ketone in terms of its directing effects. But that leaves 3 different options from the electronic effects. And so at that point, then you kind of have to revert to sterics.
Okay, that makes sense.
Okay. Any other questions on this?
I kind of had a question earlier about the alkyl groups.
Mm-hmm.
Do they become stronger activators when they become like bigger chains?
That's an interesting question. I don't know off the top of my head. I would expect it to become a little bit stronger with increasing carbon numbers, but probably not all that significant.
Not enough for like
Yeah,
what we're doing.
yeah. Any other questions on these directing effects? Bless you. So hopefully that will help you a little bit with your synthesis homework, especially when you start getting into those things that have multiple substituents on the ring. It will help you figure out what order you need to go in now. All right, so that was really all we needed to get through today. So let me go ahead and hand you your quizzes back from last time.